Seems that we are online now. So last time we had left on viewing a few fun ways to represent notations for stresses, correct? So today we are going to continue on that. We're going to talk about stress tensors and then how stresses are rotated, and now we go and find their components. So we said that the stress tensor is a matrix that represents stresses at a given point. And because it represents the stresses in all the principal directions, with the shear stress and the normal stresses, it represents the entire state of stress. So I can now interrogate that matrix at any point and ask for the stress in a specific direction that may be of interest to me. Very often we ask for the principal ones, but it's not always the case. So of course, you remember what the principal stresses are, correct? Right? Everyone remembers their soil mechanics or materials in general? No? Okay, then before I proceed, I should go and start with that then. Sometimes we make assumptions and it's not always wise to make those assumptions. Okay, so if I draw here horizontal axis that represents my normal stress sigma. And I have a vertical axis that represents, you know what I'm going to draw there? Yes, so what is this axis then?
Your stress.
Okay, and I usually represent it with what letter?
Sigma? No.
No, tau.
Oh,
Tau. Okay, well, why is it? It's a weird font. Not how I usually see tau, but it is indeed tau. And yes, the Latin T was essentially borrowed from the Greek tau, but because the capital tau and capital T are the same. So at the time that Latin borrowed its alphabet from the Greeks, they only had capitals. And you know what? You know what's even worse than the fact that they wrote everything with capitals? Can you guess what was worse than writing everything like capital? Have you read an ancient Greek or Roman text? What is, do you think for you, the most important character of all the characters that are encoded on the computer? It's encoded as a character, but you may not think of it as a character.
Zero, but maybe a.
No, we're not talking about numbers.
At.
The space, okay? Figure whole text. There is no space in those texts, no space between words. It's all continuous string of characters. Obviously, back in the day, you were not reading, nobody read silently, okay? What we do today of reading a text, and that did not exist. So everything was read out aloud. And I guess that's why it was not as important as it is today. But I can see myself going insane with a text that has no spaces. So yes. Anyways, just a little digression. Sorry about that. Just reminded of it from talking about when they borrowed letters from where, at what point in time. So yes, we were talking about the state of stress. So the principal stresses are obviously, when we get let me make sure that, oh, it's not what I wanted to draw. Yeah. I swear, I can use a computer sometimes. I have been known on the occasion to use computers effectively. Yeah, I can use the computer. Don't believe what you hear. So the principal stresses are where? Where would I find my principal stress? So yes, I would have here. Sorry, sigma one. And yeah, technically I could have sigma two and then another, there's three circles we can draw, sigma one, sigma two, sigma one, sigma. But typically sigma two and sigma three are set to equal in an isotropic kind of environment. So in most cases, we'll assume that we deal with sigma one and sigma three. What is special about those 2 points? Tau is equal to 0 on those points. Okay, so on the tau axis, we have 0. So there's no shear stress. So in any state of stress, there is one plane or a combination of 2 planes perpendicular to each other where we have no shear stresses, only normal stresses. So in the triaxial cell, we always have that case. We always know which planes have 0 stresses, right? The triaxial cell always controls sigma 1 and sigma 3. So on the vertical plane or horizontal plane in a triaxial cell, what is the shear stress?
0.
0. Okay, so always, there's no vertical shear or horizontal shear in a triaxial cell. So on the by contrast, in the direct shear box, we know what's the failure plane. We know what the shear strength is on the failure plane, but what we don't know is what sigma 1 and sigma 3 is there. Okay, we have only one point on the Moore circle. But in the triaxial test, we always control the full Moore circle. So we will often be interested by this knowledge of the of what is the principal stresses, because that simply defines our Moore circle. We can easily draw it and extract other information from it. Too many windows there. That's the one I need. So what are the stress transformations? So we have, let's say we have a different set of planes that represents another set of axes that are perpendicular to each other and at some arbitrary angle with the X, Y, and Z. So the orientation of each new coordinate axis can be known if we know the angles that the new axis makes with the original axis, of course. And we can define the direction cosines of each of these angles. Well, as you can see, it gets a little bit messy, so we start looking at things in one direction. First, we're gonna consider how do we rotate a vector? If I have a vector and I want to rotate it in a given direction, what do I do? Well, here, let's say that I have a vector, so the z coordinate is common between the initial system, and so we have the same z. Okay, we're just rotating around z. So we are rotating around z specifically. Okay, so this rotation should be theta z, because the axis around which we're turning is z. So we want to know, so the vector is the same. Okay, so we have the same vector, but we are expressing it in a new axis system instead, okay? So we're not rotating the vector, we are, although the procedure would be essentially the same, what we are rotating is the axis or expressing it on a different axis, system of axes. So what would be the projection of this onto the x prime? We want to figure out what would be that projection on x prime. But what we have is the information around x and y. So I have the projections by sine and cosine of the theta, okay? I have the cosine theta gives me the projection on x, and cosine gives me the projection on y, okay? But what I want is these red vectors instead, the projections on y prime and on x prime. So what if I take the projection, so sigma y, and I project it, so the cosine of theta applied on sigma y, not on the original vector. So the projection of this vector onto the other axes are the red lines. The projection of the vector on the original axes are the blue lines. But what I want to express is the projection of the projections on the new axes, okay? Because I define a vector by its component on the two axes, right? So because it's already defined by those components, I want to see what operation I'm doing on those components. That's why I'm looking for now the green vectors. So here I have the cosine of the vertical, and again, the cosine of the horizontal will give me the projection of their part on that component. However, I also have a sine projection, a sine component. Okay, so the green is the cosine of the projection, and the pink is the sine of the projection on the axis. And what you notice is that this part, I can add it to the cosine projection of the x component, so the sine of the y, so the cosine of x plus sine of y give me my resulting. And the sine, the cosine of y, okay? And now the direction is changed, it's against the original, so minus the sine of x gives me the resulting component. That's okay? So that's why I can say that I have sigma x times the cosine theta z plus sigma y sine theta z gives me sigma on x prime, and sigma x times the sine, it should be minus, well, plus sigma y, but, no, sorry, minus sigma x, that's what we meant, times sine plus sigma y cosine gives me, so I try to keep the sigma x first and sigma y first, that's why I inverted here the way I said it in person, okay? So that's why we start with the negative, because we're trying to keep x and y in the same order. Why am I trying to keep the component x and y in the same order in the two equations, you think?
Trying to make a matrix.
because I want to make a matrix, okay? So when you want to make a matrix, it's important to take the habit eventually, at least, even if you don't start like that, you turn things to the same orientation. So we can make a matrix, that's the rotation around Z, and that should be theta Z. Okay, I'm sorry, I made the mistake of not including the axis around which we're turning, but that should be theta Z. So of course, this is a 2D matrix, but it exists in 3D space. So because we have no rotation around Z, that will be one, okay, because we are turning around Z specifically. And so this is the full matrix in 3D space of that rotation in 2D, okay? And now if we do that, but we look at the different planes, we will get very similar equations, okay? So this is theta Z and theta X, theta Y. And this is around on the horizontal plane, but this is on the X plane and the Y plane. Okay, the two vertical walls. So you can rebuild them yourself if you want to compare to verify that we're getting to the same, but it would be a similar type of construction. Okay? And by placing things in the order X, Y, Z, you end up with these three rotation matrices. Now, for any rotation, realize one thing, you only ever, so you can multiply if you are rotating against one axis and another axis, you can multiply the two rotation matrices to have the final rotation, okay? But also remember two things, that you can rotate a vector, or which means that projected on any combination of axes, you can rotate a vector by any amount in any direction with rotating along only two axes, right? I can rotate this way and then vertically, or vertically and then, so I can select only two of these axes to achieve any kind of final rotation. So you never really need to multiply L3. You can always express any rotation by the rotation along two axes. Okay, so that's the first point you need to know. But it's not enough to know that to be able to express a set of matrices or stresses, state of stress, to express it onto another axis system that is rotated by a certain amount. Okay, because you're not just rotating it, you're taking the projection of combined stresses, and the stresses are always combined in a specific way. Let's imagine an element. You only have a normal stress acting on this element in one direction. Okay, you have zero in the perpendicular direction, zero normal stress. Okay, that's a Moore circle that touches basically the zero. You're only changing sigma one, in this case sigma y. Okay, you're only changing one sigma. This is a state like that. However, if you take that element and cut an arbitrary plane in any given direction, you will have on that plane a normal stress and a shear stress, okay? The only other plane that has no shear stress is this vertical plane, and it happens to also have zero normal stress. So this is the simplest case where you're just pulling on an element. So you want to know, so here, what is this? The force is obviously sigma y times because this is a normal stress, times the cross-sectional area A. Okay, so the length of this area, we don't care about the thickness. It can be any thickness, it's call it one. So the area is basically the length of the line A. So if we have an angle here, I've cut with an arbitrary angle theta, then the length of this line is longer than this one by the value A over cosine theta. Okay? So when I look at my projections, the stress here, okay, so we have a rotation, but because we are changing the geometry, we also have to take that into account because the area is changing. Okay, so if I have a stress acting in one direction, to find the stress in the other direction, I basically have to express that as a force, and the balance of forces means that I have to now vary the or divide this force, acting force, over this new area, okay, which geometrically is associated with the previous one. And that's an important detail because it affects the overall transformation matrix that we need. Okay. So the force sigma y times area, okay, times the cosine of theta is equal to the force in the perpendicular direction times the area over cosine theta. And so basically what you can say is that this force, the stress in the y prime direction is sigma y times cosine square theta. And using a similar approach, you can come to the conclusion that tau is equal to sigma y sine theta times cosine theta. So if you apply that more generally, you can say that your sigma x prime, sigma y prime, and tau x prime y prime can be expressed in terms of the sign around that single for that plane specifically. And it's because of those transformations that when we want to find the stress acting on another set of coordinate systems, so we take this, we have a matrix that represent the stresses, acting on one set of axes. If I want to express the same matrix on another set of axes, I have to take my my cosine matrix, my cosine matrix, which contains basically my rotations. But it's not just the rotation. Okay? I have here the transpose of the rotation. Okay? Because of these combinations. Okay, so you see I have sin theta, cos theta, sin squared theta, and cosine squared theta. Okay, because I need to find the projection of the force. It's not a single rotation. I have a rotation, but then I project and I multiply by the effective area, which changes depending on the direction in which I take my slice. Okay, it's because of this that it's not just the rotation matrix times the state of stress that will give me my state of stress on another set of axes. If I take the rotation of the two axes between them, I have to multiply by the cosine matrix and multiply by, here it's the transpose. It's really the invert that I want, the inverse of the matrix, because I'm dividing by the matrix, okay? Because I had times cosine and divided by cosine, right? Basically, I'm basically using both operations. But it happens that because those rotations, those three axes are perpendicular to each other, all the operations that I do on them when I do the inverse, it's always equivalent to a transpose. But computationally, if I have to do a matrix inversion, it's computationally intensive. I have to do lots of mathematical operations on the computer, while a transpose is just remapping it's switching the indices I and j and just remapping the coordinates. Okay, so the transpose is a very simple operation. I don't even need to physically use a different array in memory. I just flip the I and Y when I address any one item, and bang, I've done the transpose, right? So I don't need to actually do a transposition directly if I don't want to. So because of this, in this particular case, we use the transpose instead of the inverse, but it's the equivalent of having an inverse thing. So this is how you will do a transformation of a state of stress properly. And you could do a trial and error approach if you needed to find the angle between two matrices. You would have to change the cosine values in between to find them. Now, another thing to know is that at any point T, as we said, there will always be one plane or one combination of two perpendicular planes where the shear stresses will be zero. And we said that that is called the principal stress planes. Okay, so that is usually what we are interested in finding. Okay? And of course, we often need to know their magnitude and orientation because it will simplify calculations. There's different ways of finding them, but you may recall that there was I don't know if you remember how to find the eigenvalues of a matrix. And so a matrix, there's a scalar times a matrix. You will always have, so if you subtract the scalar times the unit vector matrix, you will have always a case where you have a resulting set of vectors where you that is non-zero. Okay, so you have the non-trivial solution. Anyways, the point is that when you do the operation to find your eigenvectors, you can express your operations at the end of all that with, so if sigma here represents your the terms of your eigenvectors in your case, in the case of a state of stress, you will always find that the three roots of this polynomial will give you your three principal stresses. Okay? So if you solve for this cubic polynomial, you will always be able to find sigma 1, sigma 2, and sigma 3 by solving this equation. And so based on this, the thing is I1, I2, and I3 are called the stress invariants. Okay? And they have simple definitions. The first stress invariant, so notice that, very important here. Okay? If this question comes up, if you have to compare two states of stress, you don't need to necessarily determine what is sigma 1, sigma 2, and sigma 3 for all cases. You don't need to solve the equation. All you need to show is that if the three stress invariants are equal, obviously you have the same state of stress. Okay, so if all you need to do is demonstrate that two states of stress are equal, they will have the same stress invariance. Now, the first stress invariant is super simple. And it's just the sum of the diagonal. Okay. And it is, of course, because it's the sum of the diagonal, it's also equivalent to having the sum of the three principal stresses. Sigma 1 plus sigma 2 plus sigma 3 gives you your first stress invariant. So already, if you have two states of stress and someone comes and asks you, are these the same state of stress? If you do the sum of the diagonal and it's different, you say no right away. Okay, so you solve each stress invariant in increasing order of complexity, and that will let you determine if two states of stress are equal without necessarily solving anything or going into complicated math, right? So you start with the simplest, and this is the simplest. If the sum is different, you say no. The second stress invariant, it's basically the determinant of the three possible submatrices that you can make. You add the determinants. Okay? So you can think of the same thing. The first stress invariant was also the sum of the determinants, right? You took you found the determinant of this matrix plus the determinant of this one plus the determinant of this one. It was a one by one matrix. Okay? But that's basically what you did. Now what you're doing, you're expanding. You're expanding to a 2 by 2. So you find the determinant of this matrix plus the determinant of this matrix. Okay? Plus the determinant, and now you have the sigma 3 and sigma 1 of, for the last one, sigma 1, 1, 3, 3, 1, 3, 3, 1. Okay, so you're basically doing the same thing, except, so you do the sum, you find the determinant of the one by one matrix, then you expand to 2 by 2. And of course, what will be the last step? What will be I3 based on this? It's the determinant of the whole thing. So you do the determinant of the one by one matrix that contains each of the principal stresses of the diagonal, the terms in the diagonal. Then you expand to a 2 by 2. You find the sum again, like you did for I1. And I3 is the same, except you only have one matrix that's 3 by 3. Okay. So that's basically how you find your stress invariance. Okay. You remember how to do the determinant? If I want to do the determinant of what is the determinant of this?
Sigma 1, 1, I have sigma 2, 2.
Yeah.
Yeah. Obviously sigma 1, 2, sigma 2, 1 are equal to each other, so that is sigma 1, 2 squared. And if I want to do the determinant of a 3 by 3,
Sigma 1, 1.
so sigma 1, 1 times the determinant of,
Sigma 2, 2.
yeah, of sigma 2, 2, sigma. Exactly, minus, because so minus sigma 1, 2 times the determinant of, and this time we remove this column.
Yeah.
This row, so sigma 2, 1. Sigma 3, 3. Sorry, and sigma 3, 3. And that's sigma 2, 3. And sigma 3, 2. Sorry, did I say sigma 3, 1? I say it should have been, yeah, 2, 3 and sigma 3, 1. And plus sigma 1, 3. Times the determinant of sigma 2, 1. And so that's how you end up getting to these development. Now, the fun part is that if you have the principal stress, so this is why you like to do triaxial tests in the lab, right? Because doing analysis and fancy things numerically when you do a triaxial test lets you say that sigma one, because shear stress is zero in a triaxial test, you're working already on the principal stresses. So how do you find I1, I2, and I3? Well, I1, again, sigma 1, 2, 3, that's easy. But I2 is just the product, the sum of the product of 1, 2, 2, 3, and 3, 1. So the product of 2 by 2, the diagonal terms. And I3 is just the product of the diagonal. So the principal or the stress invariants are super easy to calculate from the principal stress matrix. I'm gonna lie in the following slide, but because we're not gonna spend the time to do iterations to try to find the angle, but you could do it by trial and error. What we are going to do is to find the principal stresses in the exam. Okay. So important again, the values of the stress invariant do not change if the coordinate system is changed. So if you are asked if two states of stress are equal to each other, what do? If I ask you if I give you two states of stress, I ask you if they are equal to each other, what do you do?
Compare.
Compare what?
Invariant.
Invariant, okay. In what order should you go in comparison? Should you calculate all three stress invariants for both matrices and then give me your answer? No, you start by, you do the first stress invariant, you compare. If it's equal, then you proceed to the next stress invariant. If it's still equal, the two are equal, you go to the third stress invariant. And if there's all equal again, you tell me it's equal. As soon as in that process you get to a value that is not equal, you say, no, it's not equal. Now, we're talking about equal. Okay? I want you to take equal with a grain of salt. And this is something that you can practice by making your own matrices, rounding up to appropriate values. And when you round up like that, the stresses that you measure are always rounded if you are measuring actual stresses. What you notice here is that you have a summation. And there might be some error. What do you do here? A product, what happens to the error? It gets, multiplied, squared. And what happens in the third term to your error? It's cubed. Okay? So do not expect to have an exact value. And this is where playing with numbers, rounding off different and play. I cannot give you a universal answer. What you want to do is play with numbers and a certain range of values, play with rotations, start with the same, start with a given stress matrix, rotate it in a given direction with the equation we saw with the transpose, and now do the analysis of stress invariance with rounded values to different degrees of those matrices, okay? And see the agreement of the stress invariance. See how much they start disagreeing, even starting with equal, identical states of stress, okay? And then you will start having a feeling for how much disagreement you can tolerate before you say that two states of stress are different. Okay? It's important to get a feel for those things. And the only way to get a feel is to apply your transformations. And maybe we will do something like that. Okay? So, but if I wanted to find, first, we're gonna find the principal stresses of this particular matrix, just for fun. What would be the state of stress of this matrix U? How would I go about solving it? Finding the state of stress. Um, we had a cubic here, right? Okay, so how do I find, so if I had my initial matrix, which is minus 10, 9, 5. Nine, 0, 0, 5, 8. So I would have first to calculate the three stress invariants. And with the three stress invariants, I can then calculate my my value. So let's go and start playing with these on our own. So original matrix, original mother. 508. And 95, 90. Okay, so we have here our matrix. So what is our first stress invariant? That plus that plus that, right? The third stress invariant here will be m det of the entire thing. And our second stress invariant will be the determinant of this plus, or can do it manually if we prefer. This times this minus this times that. We'll write them as separate values and then we'll add them together, okay? And then we have the determinant of this times that minus this times that, right? And then for our third determinant, we had column 3 and 1. So it would be this times 3. 5 times 5. Correct? If I did not make a mistake here, this should be our I1, I2, and I3, correct? I did my sub matrices, sub determinants first, and then just added them up. Or I could just say it's this times that minus this, that plus this times that minus this times that plus this that this times. So we have our three terms. So going back to our equation, we now want to solve for minus I1 sigma squared plus I2 sigma minus I3. All done, right? So you can solve the cubic for me? How do you solve a cubic?
So sulfur.
That's how do you solve a cubic? You know, I think the fourth degree polynomial is the only one for which there's a closed form solution. Anything after that? But it's very complex. I think everything after that there has no closed form solution. So let's assume that we don't know. I don't know. I only know the solution to a 1 degree and second degree polynomial. The square I can solve. I never remember the method to solve a cubic. So what do I do to solve?
Actually, for me, I know there's a function in Excel. There's
How does that function work? You have to program that function. We are here in the numerical method class. We want to unwrap a little bit sometimes those black boxes. We want to unwrap them sometimes because it's fun. We love them. We love black boxes, but they're fun to unwrap sometimes. So how does the nonlinear approach work?
You assume one,
you have to assumption.
You remember Newton's method? Okay, Newton's method will work whenever you can find a derivative to a function. And you can always find the derivative of a polynomial. Okay? Now, the other thing that is fun about polynomials is that even if you don't remember the quadratic, you can use this approach to find your root, the two roots of a quadratic, if you can solve for a 1 degree polynomial. If you can solve for a straight line, then you can find the 2 degrees. What's important to remember is that what is the derivative of a polynomial or any function?
tangent to,
No, but what does it mean?
Really?
What is the meaning of the derivative of a function? The derivative of a function is basically duplicate the. If I have an axis, let me make it even better than that. Okay. So if I have my axis system and I have, so what's the shape of a 1 degree 1 polynomial?
Straight line.
It's a straight line. What's the shape of a degree 2 polynomial?
Parabola.
It's a parabola, right? So. Actually, that's, I should have made it, put up something in exact center. Okay, I'll try something else. Draw a parabola with my drawing tools that I have here available. So I shall draw a parabola with the drawing tool that I have here available. So how that would be the best way to draw this. Keep that there for the moment. Close enough to a parabola. It's not really a parabola. No, it's not a parabola at all. Should have done it mathematically, right? Would have been, I said, okay. What would look like a parabola? Maybe. That's the best way to do a parabola. Yeah, that looks more like a parabola, doesn't it? That's more the shape of a parabola. So, what can I say about this parabola then? What would its slope look like? And what would its derivative look like?
Straight line.
A straight line, right? So in particular, where would the straight line cross zero?
Minimum.
So if I find a point where the slope is zero here, yeah, so then I have my, so if I find the derivative and I find where it's equal to zero, I find the minimum. And if I find the minimum, so the straight line of that parabola will have a given slope and would cross zero there, so it might look something like that line, right? Where it's negative because before that it's negative, right? So it's below zero and zero here, and then after that it becomes increasingly positive. So that's the slope. And it makes sense. So, okay. So if I want to use Newton's method, you may remember that you need a seed value, you need an initial value. If you have a parabola, you have two roots. So if you have two roots, you need to start approximating from two different directions, right? If I use any guess and both are on the same side, I will converge to the same root and my conclusion will be, oh, I have one root, but it would be wrong. However, with polynomials, if you analyze the derivative, you can tell, you can choose where to start your approximation. So in this case, I would find my root and I would say, well, I need a value that is left of, that is smaller than that value and one value that is larger than that value. Okay, so I can say if this is absolute values, I can go halfway between 0 and there, and then, yeah, you can play and choose to have enough separation to make sure that you will converge to the two separate roots. Okay, so you can identify that point. What does a generic cubic look like? What does a generic cubic look like? Right, you agree that this is a generic cubic? Right, if I were to put this here, I have potentially three different roots. So how could I figure out where? So I need to analyze before I can find my roots. I need to make sure that I will not have two initial guesses. So I have to start with three separate initial guesses. If I'm going to use Newton's method to converge, I have to start with three initial guesses to converge to three different roots, right? So I would ideally want to identify where so I find my two maximum and local maximum and minimum. The same way as before, right? That will give me a location for my division. So if I find the two roots of H, I'm gonna make it a bit fatter. Sorry, I need to make sure that I'm here. So I find if I find the parabola, so the derivative of that cubic will be this parabola. To change the color, so they're easier to identify. So let's make this one yellow. Let's make our parabola. No, that, are they different enough? No. Okay, so the parabola gives me my slope, right? Let's say that parabola represents the change of slope. So I start with a positive slope, so that's a positive slope. It becomes negative after this inflection point. I'll have a negative slope, which becomes inflected here, after which I have a positive slope again. So this parabola represents the overall change of slope of my cubic, right? So if I derive my cubic, I get this parabola. If I find the two roots of the parabola, I can find my initial seed. I will say start with the average value of the two roots. And then the lower point, the two extreme for all intermediate, let's say you have a polynomial with multiple roots. The intermediate ones, you can always find the average value, right? It's equidistance from the two edges, so it will find the root that's in between those two, okay? And then from the two edges, then I could go say halfway between 0 and here, or and here maybe halfway over there from the distance between there and there, so that I can do some, exercise to make sure I have enough range, that it's not too close. And so I use a seed on that side of this root, a seed at the midpoint between these two roots, and a seed on that side of that other second root. And now I have three roots. I have three seeds that I use to solve Newton's method that will give me the three roots. And if two of these roots happen to be the same, then fine, it's okay. Okay. So that's how we will use Newton method to solve for this. Okay, so here we have our polynomial. So we have our parameters. So if I have A, B, C, D, A is 1. Right? A, B, C, D. B is minus I1. We should probably center these, otherwise we're gonna get confused. See, already I got confused. C is I2.
It's 186.
Oops. And D is minus
648.
I3. And these are the parameters of the derivative. So what's the derivative of this term is
3 sigma
3
squared.
squared minus 2I1 sigma plus I2. So this is the quadratic with A, B, and C. So this is cubic quad. And so the cubic is 3. Minus 2 times 1. And that's I2. So the two roots of the quadratic is minus b plus square root of let's say b minus, let's do that. Call this b. I call this a. Okay. It's one c. Yeah. CS. We have here b plus square root b square minus 4 times a times CS. Divided by 2 times a. And here we have plus or minus. So the two potential roots are at 7 and 8. And minus 8, sorry. So the the three seeds that I would need would be so the minimum of these two values. I will add the minimum minus the distance between the two values. I think that's a good, let's say -1 minus max. Oh, let's say min. I'm doing something that is generic, okay? Min is the -1 minus the distance is the max of the two values. Minus min of the two values. Right, that's distance. And -1, just in case the two values are the same. So we at least go -1 and +1. The middle would be the average of these two values. The max +1 plus the distance between the two values. Okay, so these are three seeds that I can now use in my Newton's method. I will call this AC, BC, CC, and it's the S and BS, but we are here. So here we now have sigma. We have F prime. And we're going to start with our initial guess for sigma. What is the function? The function is the cubic. Okay. So the cubic is AC plus BC times sigma, right? Plus CC times sigma squared. No, it was sigma cubed, sorry, yeah. It's AC times sigma cubed plus BC times sigma squared plus CC times sigma plus DC. Then I call this DC. I had not. Okay, so I have here the various values of interest. And so F prime is what? Is A times sigma squared, right? And X squared plus I recall J plus BX, so J squared plus BX plus C. Right? So based on Newton's method, what is the what is the next value of sigma in my attempt? Newton's method. I have any function. I have an initial estimate of the root. Or I should start here, say it will be easier on me. I take the slope at that point. Where the slope finds zero, I make my next guess, right? So the slope is, of course, f prime. So here, my initial guess x. At which point I have f of x. And so the slope is f prime, but is equal to we approximate the slope with delta f over delta over delta x, correct? So if I have here if I have f of x zero and x zero, what is f prime? F prime will be given by so I will assume that my next guess will be the correct solution, right? So it will be 0 minus f of x for my initial guess. Correct? Because I assume that x here is 0. This straight line intercepts the next guess will be where it is 0. So that on that next straight line, the vertical is 0. And so I have here x for the next guess minus x. Right? So that is my the expression of my little of my equation there. And it's because of that that I can just simplify this and say this is minus f x naught. And I can multiply on the other side. By this, correct? And that's how I have, so I divide now on the other side by f prime. And I can say here plus x naught minus f, or just simply the previous guess. The next guess will be the previous guess minus f over f prime. And that is why I was able here to say that my next guess, so the next guess is the previous guess in blue minus f red over f prime in pink. Okay, so that's all that this is. So that's based on the first guess. What I will do is do this And this time I will use the second initial point. And we will set this up the same way. With the third initial point. Of course, the next guess will be the same function on both cases. Okay, and we will. Here we can see that sometimes we may need to converge a bit more. It depends on how much we've rounded off, right? It depends on how many decimal places we want to keep. Yes.
I kind of stopped following when you got your minute back, so a little bit back.
Okay.
I understand the principle behind Newton method. But the idea here is we're just converging on one value for sigma, right?
Yeah, what we're trying to say is that our three values for sigma, we have here -16, 24, and 7.5. Basically, or 7.4 seems to be our conversion point. Because it seems to be flipping up a little bit, so sometimes what happens with a cubic, when you have a cubic, you may find that this middle, generic cubic may have this middle part here very flat, almost horizontal. When you have this part like this, you may find it's very hard. So you'll have to have some critical, that's why that middle point where it's probably a very flat cubic. So sometimes we convert on one side and it starts moving and then, so it's 7.4, but you can see that because it's so flat, we don't have a sharp definition. That's why we get this table, which is long.
So it's something like this. I'm just gonna say I'm a bit lost in the calculation. And basically, this is a step where you generate 7.28 and then the bottom row. I understand everything after that, but I just don't know the code to do that.
This one?
Yeah, that's.
That is what that's just the quadratic.
The answer.
Mine, sorry, I assume that everybody remembers from high school.
Oh, yeah. That's the.
Yeah, that's A minus B plus or minus.
Okay.
C minus B plus or minus, so this is plus, this is minus square root of B square minus 4AC over 2.
Okay.
That's-
I was just writing it.
You could have done the same way that we did with Newton's method. You finding the derivative, it would be a straight line, and then you find the root of the straight line, and you start with a seed on both sides, and it would have converged numerically. So if you want to do that more generically, you can.
So say we have this matrix right here, right? This isn't something we would see in a controlled environment, would it be?
I mean, this is one thing that you might do yourself to solve. So you might do this programmatically, if you wanted to implement. As I said, my goal for this course is to go through as much hands-on as possible of different steps that you might do if you were coding it, okay? So that you can see one approach. I mean, for the cubic, to be honest, there is a closed form solution that you can find, and it's probably what you would do to implement to solve a cubic. There's also other ways to find the roots of this problems with the in matrix algebra, but this is one way that you can find it, for which you have easy tools that doesn't need to get too complex, and you can solve it fairly quickly. Okay, depending, again, always depending how much you need to round off, okay? This is one thing also. I noticed here that I kept a horrible amount of decimal places. You don't need to keep all these decimals. Okay? If you were to round off your result here, did I round off? I mean, do I need a fraction of a kPa, a small fraction? So let's say a hundredth of a kPa is all I need. So I round the result to 2 decimal places. Then you see how that I converge faster. And I bet you this one would benefit from the same treatment. Okay, when you're trying to find actual solutions, and we're converging to a slightly different value than before, so 7.7, 0.6, 0.7. It's still a little bit floppy, okay? So it's not a clean route, but you see, well, that was fast. You converge faster when you round off. You may not get to 0 exactly. Okay? But at that point, what's important is that the difference is close to each other. Yes.
I want to start from when you define the lower initial gas and the
Yeah.
maximum initial gas. Yes.
Yeah.
How you define this?
It's arbitrary, right? Well, I know that the minimum must be smaller than the minimum. Okay, so I find here my 2 roots of the quadratic. So I look at the minimum and I know that I must be smaller, my initial guess must be smaller than that. You don't want to be too close because you can get across because of round off errors and so on. So that's why I said -1, because in case the 2 values are the same, I put that -1 to make sure that I start on the left. Okay, so this is arbitrary. I could have put in any value there. And then I say the max minus the min. So I take the biggest minus the smallest to get the range. I say, I put that distance between the two. I say that far away from that side and -1 to make sure I don't get 0 if the distance is 0. And I do the same thing on the other side. I said, but it's arbitrary, okay? This is just my way of this is really my way of saying you could use any other algorithm that you might choose that makes sure you are on the right or on the left of the minimum and maximum. Okay, this is just one way that I made sure that I started on that side. And so you have latitude, but so this is one way that you can use Newton's method. Newton's method, you should never forget it. Okay? It should always be your friend, not only in masters and so on, but as a practicing engineer. It's because it's corollary the secant method. The secant method is like Newton's method, except you don't have a function. Okay, you can use it with experimental data. So what do you do when you don't have a function that you can derive? Well, instead of making an initial guess, you make 2 initial guesses, then you approximate the slope, okay, by finding the increment. And so you start with 2 values and then you keep using Newton's method using the previous slope. So you calculate the slope based on 2 consecutive values. Okay, so you don't need to know the function. The beauty of the secant method is that this does not need, it can be a black box. So it can actually be an experimental result. So instead of covering a whole number of values for experiments, you use your experiments, you do 2 initial tests, and you want to find the optimum value. So now you use the results of those optimum tests to predict what should be your next test to get the 0 of the whichever parameter you want, and then you can converge and see that you get it.
So usually using the linear finite element analysis.
Yeah, when you do finite element analysis, exactly. you want to find, or slope stability analysis, you want to find exactly a factor of safety of so much. So you set the factor of safety of 3.5. What slope do I need? So you change the slope and you calculate the factor of safety and until you get the slope that you need at the factor of safety that you need without. So that's the beauty of the secant method. Okay? So not just in research or to solve problems internally, but as a general design tool. Okay, and we will be using it in 4108 a lot. Okay, so yeah, I love the Newton's method and the secant method. So just be aware that you can use them also in this very convenient way. Okay, and we would do a trial and error to find the cosine values. Okay. Now we're going to talk about octahedral planes, which is something that will come often also when you do your literature reviews for your little report. So the octahedral plane is a plane that is that is equal angle with each of the principal axes. So basically you're 45 degrees with all the axes. If you make a line in a diagonal line in the space, so if so if you have your let's uh station. So oops, if I were actually. So if I'm looking at it, it's basically the line that's coming in my face, okay? Or if I were to change the plane angle subtly. Okay. I turn it a little bit more like this. So the octahedral angle plane would be the plane perpendicular to a plane. Right, so imagine that you have a plane like that. Okay, so you have 8 octahedral planes that are basically so 45 degrees with all the principal angles. So if you were to draw a line equidistant on each axis and join them with a triangle, that defines the octahedral plane on each of the axes. Okay, and that octahedral plane, you can calculate it well from it's basically the 1/3 of the sum, so it's the average principal stress, basically. It's 1/3 of the sum, it's 1/3 of I1. So this the sum of the three principal stresses. So it's the average normal stress. You can think of it as the average normal stress on a point for the hydrostatic stress. You can also calculate the shear stress acting on the octahedral plane. And the shear stress acting on the octahedral plane is a little bit more complicated. It's much simpler when you use the principal stresses, but even then, it's more complicated than the octahedral stress. There's also a different notation. So if you take I1 and I2, so 1/3 of the square root of 2I1 square minus 6I2, it's equal to square root of 2/3 of J2. J2 is another stress invariant for shear, but these two terms are essentially equivalent. So they are practical invariants, the octahedral stresses, and they are useful to establish failure criteria. Okay, and different numerical methods that you may encounter. So sometimes you may prefer to indicate the octahedral stress as the spherical or hydrostatic part of the stress tensor. And therefore you can determine the deviatoric part. So the stress tensor at any point is the spherical component plus the deviatoric component, okay, or the average peak and the shear equivalent. Okay? So if you define sigma m as that hydrostatic component, which as we said is the average of the three principal stresses, or 1/3 of I1. So basically that tensor is a subtensor P, which has only the main diagonal and all three values are the same. That's your hydrostatic, your average stress and one component. And the rest is what is called the deviatoric stress. Okay? So sigma x minus sigma y. So the deviatoric, you have to subtract the spherical stress from it. So basically you subtract the octahedral stress from it to get the deviatoric stress. Now, if you're dealing with the principal stress tensor, so you are dealing with triaxial test, then it would be sigma 1, sigma 2, sigma 3 minus that sigma component. And of course, we said that there were different stress invariants also in terms of the deviatoric stress, and the J2 that we saw before is that term 1/3 I1 squared minus 3I2. Okay, so you can define J1, J2, and J3. J1 is the easiest one to calculate. Okay. I would expect that, but since we're not doing an exam, I won't be expecting you to remember it for the exam. Otherwise, I would expect you to remember it for the exam. Now, as I said, the fact that the three roots are the eigenvalues of our system means that if you're using something like MATLAB or Octave to do your analysis, there's a short way of finding your principal stresses. And we're gonna see a little bit of it right. Let's take a short break. What time is it now? Is it almost 9?
Yeah.
Oh, I took longer than I was hoping for. So let's take a short break and we'll just do a quick overview of MATLAB, well, actually Octave, when we come back. And we'll see how to solve your three eigenvectors in a simpler way. We'll figure out your principal stresses. All time flies when you have fun. Apparently, I was having fun. Not sure about you guys, but I was. Oh, bitch. Everyone knows how to access student labs on the online. You can go to the student labs in the different physical labs on campus, but
Do you have the link for your past YouTube videos?
oh, I didn't post it. Oh, I must have done it in 4108. Yes, I will be posting that. Well, if you go to Ottawa or you student lab, it used to be, okay, let's see. Labs, Ottawa.ca should take us to, yes. So if you have the native client, it's better if you can download and install on your computer because you can share a folder between your computer and the university, the labs. Right? If you're in the computer labs downstairs, everything's done automatically, you just log in, right? But if not, launching native client is better because you can select in the native client, you can say this folder, I want it to be also available online when I'm online. So whenever you do things, you save things in that folder and it will be saved on your local computer.
Cloud.
Hmm?
It's like a cloud.
Yes, but see, if you go here, you have access to these, okay? But the difference is that I will not have access to my like uploading and downloading files a bit more complicated if I do it this way, okay? So MATLAB should be available here, right? That's why I logged in here. And I'm looking for, do we no longer have MATLAB here? Oh yeah, we have it. I'm just blind. I'm blind. You can laugh at me. It's allowed.
Ah.
Yeah, you just calculate this one value.
Yeah, from Sigma.
You know, from, oh, so, oh, yeah, from Sigma, yes, sorry. I think that was Sigma, but there was a change of font at some point in the past and it became, because in the early days, I think when I first made this, Unicode, I may not have used Unicode, I may have used symbols, and then the S was Sigma. And I think then the symbols changed, I started changing, but I must have forgotten. Thanks you for pointing that out. I have to change it to fix it. Oh, another.
This free. Sure. If you get this.
That one I probably just copied from somewhere, but I would have to read. This is from the shear.
I think it's about something about shoes.
Yeah, it's if you were to solve the matrix.
This matrix.
Yeah, the matrix was subtracting sigma one, yes. The same way we found sigma one, yeah, you do this, but instead of being the sigma matrix is the S matrix. The deviatoric matrix.
That matrix is this formula is come from.
Yeah, we're subtracting I one from, basically, we're subtracting the deviatoric stress from the matrix, right?
Yeah. The matrix is this.
From sigma, we're subtracting sigma m, subtracting p from sigma to get S.
Yes.
So if you take the S matrix, you use the same sigma cube minus I one. So using the same approach, but you find I one, I two, and I three on the resulting S matrix rather than the original sigma matrix.
Oh, okay.
Okay. And if you do the algebra to express it in terms of with keeping I and I one and I two and I three, then that's how you end up with those more complicated terms. Because they're subtracted, but some of them was squared. It makes it a bit more complicated in that sense. Okay, okay, so here we have that. And this is octave. I was able to just install Octave on this computer because you can get it on online, which is fun.
That you use that have the link that you use that have all the softwares.
From Uottawa, that's ulabs.uottawa. ulabs. Oh, sorry, student labs, studentlabs.uottawa.ca. I should add that in the links for the course. Add it immediately to links, okay? To the link. It in French, it's Labo étudiant. Okay, so using MATLAB is generally fairly simple. Okay, so you can define variable by default. isn't a problem. Whatever you write here, also keep in mind, you can save it in a plain text file. A plain text file, you can use Notepad or use a better text editor. I highly recommend if you want to install a little text editor that's super simple, that works with different programming languages, to use Genie. Genie is quite simply a great little tool. If I go to Genie, it's just a text file. It will save as a plain text file. The kind of thing that you can use. You don't want to use Word or any fancy word processor like that because you need it in plain ASCII file format. So this one will recognize also different languages, and if you go to documents, you can see file types. By default, these are all the scripting languages that it recognizes, and it can do syntax highlighting. See, it has MATLAB octet source file. It can recognize those already. I think it's .mat, the default extension for those. And it will recognize them automatically and do some syntax highlighting for you. So it's a pretty good little text editor with syntax highlighting. Highly recommend. Now you can download things directly from here and install them. You may have noticed that I have this little thing here. This is portable apps that lets me save a folder basically and carry it on a USB stick if I want, and have installed apps in there. So most of these apps are also available from the portable app site. So if you're interested in having carrying with you a few tools like that you might want to use at different locations, like this calculator, which is quite powerful. Then yeah, it's nice to have this portable apps. So there's two ways to install this directly from this site or portable apps. Okay, so you can install the portable apps and then it will let you export to USB sticks the apps that you want, and you can make different little portable files with it. It's really, really, really quite awesome. I just love it. Okay. So and yeah, of course, new Octave is also something you can get from here, and in this case, I installed it. Octave is not available on portable apps, so it's something you have to install whenever you do. So you find variables quite easily when you're yeah. Oh, by the way, if you want to save files on the web browser one, you have this open file transfer panel. Okay. Which lets you choose files from your computer locally to upload. So let's say I wanted to upload this. Oh, I would have to choose them like that. And now I could access them in theory now from my app by going somewhere apparently. Not sure where it's my documents. Well, I just uploaded from the local computer. Is that what I did? The file transfer panel. See, that's why I say that if you have the client, it's a bit easier. I am not sure. Oh, all files, all files. Yes, so it uploaded the file to your document. So if you do this and you click on this option here, the file transfer panel. When you add files here, it will upload to the cloud computer on the My Documents. Remember, when you want to transfer them back, you have to say, go to your app that you're using. If I recall, if I want to download back the file that I uploaded. Let me try to figure out how you download. Control Alt Delete current. How you're supposed to download. I don't remember at all how you're supposed to download. Best. Drag it up. I'll click choose files button, file upload to both. Now, how do I download? Transfer files, you look no, that if uploading it doesn't tell me how I'm supposed to download. You notice, right? I'm trying to fix for you the thing. We're gonna leave it here. Take too much time, but if I want to download from the cloud, how do I go about it? Upload, drag and drop. Okay. How do I download though? Does anyone know how to?
You send an email.
I'm pretty, yeah, I'll have to look it up. Just in case some of you are using it regularly. I'll have to look it up because I'm pretty sure I was able to download last year when I tried this with my undergrad class. Drafting class, I went through this. And I know I had to open the file manager in here, copy. Upload, and how do you download? Fail to see how uploading is useful if you don't have downloading. Anyways, we're not going to be saving right now, so I'll try to figure that out for another time. B equal 3 times A. See, it's you just define the variables by typing the variable name equal and bang, it's super easy. Barely an inconvenience. Um. and so you can do all these operations. And also define a variable fairly easily. What was our variable that we had before? Okay, so call our matrix. Minus 10, comma 9, comma 5, colon 9, comma 0, comma 0, colon 5, comma 0, comma 8. I believe that's how you define a matrix. Okay, so comma separates column, colon separates rows. And you can have, if I remember, 1, 2. So you can give the index. The way to get the this sub matrix. So that's 1, comma 2. So it will give you so. And so you can even put a sub array as pointers, and it will give you the sub matrix. Okay, so you can see that if I wanted to calculate I1, I could say is equal my and if I want to say I2, I could say it's the, okay, so if I say the I3 is equal to the determinant of M, right? And I2 would be the determinant of M 1 and 2 plus the determinant of M and we said 2 and 3. M 1 and 3, 3 and 1. I probably mismatch a parenthesis. See, so it's so I2 is equal to the determinant of M 2, 1, 2 plus the M 2, 3, 3 plus the determinant of M 3, 1, 1. Okay. So you can find your determinants of submatrices that easily from this value. Also, you could say I think it's IV. Oh, yeah. So if I look for the eigenfunctions, I get 3 values that correspond to, I don't remember, was that what we got for our values? No.
That was 7 and
Minus 16, 0, 4 and 10. So we made a mistake somewhere, guys. We got one okay. Minus 16.08 is okay. The others are both incorrect, so we made a boo-boo somewhere. It can happen. I'd have to check what we did. But this is the eigenvalues of the vector is basically what we were looking for, okay? So it's the direct result of our search. Now, how would you do those things in Octave? Well, in Octave, it's a little bit different. See, your matrix, you would define it this way, minus 10, comma 9, comma 5, colon 9, comma 0, comma 0, colon 5, comma 0, comma 8. Okay. And so I1 is equal to M11 plus M22 plus M3. I3 is equal to the determinant of M. And I2 is equal to determinant of M. We said 1, 2. 1, 2. Of course, you could save that in a matrix, right? I1, I2, and I3, or in a function. You can make functions, and that call to determinant would be super easy to call. Plus determinant of M. 2, 3. Determinant of M. 1. 1. Or you can find the eigenvalues of M. As you can see, there are widely different programs that give you wildly different values. And no, so in their use, they're fairly tame, very easy. Octave uses exactly the same syntax as MATLAB. Okay? But you can download and install it on as many computers you need. There's also is it called Octave Forge? Octave Forge is full of add-ons. To program Arduinos, data smoothing, CGI, audio, control, icon, finite elements, fuzzy logic, financial, databases, geometry, image processing, new scientific library. I mean, these are groups of packages. These are the category. Call. Okay, Forge, a good place to go and find all these add-ons that we all understand. But here you have individual packages and stuff. Okay. So that's the kind of thing that you can install. Okay. So I have here go over some of the same things. You can also start Octave from the command line, by the way. That's on the command line or an old interface. So I won't go over this. You can go over the slides if you want. It's important. You saw how to use them in person. And so we should be able to have fun playing with it. And so if we have time, we'll try to do something with it, but if not, we'll really concentrate on the spreadsheets. But the tools that we can use.
I understand, like, the value of sigma one, sigma two, and sigma three is the eigenvalue of this matrix.
Yes. It is the eigenvalue. Okay, so basically, if you were to solve manually the eigenvalue, you would find that you end up with the that cubic function. So we didn't go through that process, but that's how you would end up with that cubic function to express it. And so,
But can we do that like with a spreadsheet though? Like the same thing we have done.
I don't think the function eigenvalue exists. I think I looked at it, but I don't think it exists in the spreadsheet. If I find an eigenvalue, I might be wrong, they might have added it over time. The last time I checked. Eigenvalue. No, I don't think so. I find the determinant, the inverse, the multiplication of matter, and the matrix. But you don't have eigenvalue or eigenvectors of the matrix. So on the spreadsheet, you would have to use a bit of alguma coisa. Ele do quick. That's why I wanted to show you different ways of achieving the same thing. I highly recommend if you are going to program things, learning Octave as a programming language would help you a lot because you see it has integrated as part of the basic functionality, very advanced matrix operation things. So that's not something you do not have to implement yourself. Okay? You can still use Newton's method for different kind of solutions to problems, but there are things that you do not have to implement. It's built in. So why would you go out of your way to make your life miserable? Unless you really need performance, because you do a lot of, but keep in mind that I mean performance because you need to do some operations that are not matrix operations. These languages are very optimized to perform matrix operations. So whenever you call a matrix operation, you will find that it will give you a result much faster than if you have done the same thing yourself by other means. And even using another programming language, even an efficient programming language or fast, you may not be optimizing it as these have been optimized for matrix operation. Now, if you need to do things that are not matrix, that have a lot of loops and things like that, you might lose time. But so sometimes when we discuss the finite difference method, there's different ways of doing things. Some is step by step calling the previous term. If you do that, you can express the same operation as a matrix. Or so if you use another programming language, it's probably more efficient to just use the memory. We use less memory to express it as a vector and just call the previous one and calculate each step like that consecutive step. But if you're using Octave or MATLAB, it's more efficient to express it as a matrix and do a matrix operation to call the to apply the changes, because matrix operations are done more efficiently than if you were to loop the terms. Okay. So sometimes you have to keep that in mind when you're using different. And so Octave is something you can install. I highly recommend it. Want to play around with a little bit of programming? It's a very efficient programming language. With Octave, you don't have to worry about licenses. Okay, so it is Octave. We just did something simple, but you can see that it's already pretty. Okay. So go forth, have fun, enjoy your party time tonight. I can see it in your eyes, you're just waiting to get and go home and. I'll see if I can figure out how to download the file.